Hello students, welcome you all. Now today I will start the topic pericyclic reactions. So this is the one of the branch of organic chemistry. Usually in organic chemistry we read about the different mechanism of the reaction where the nucleophile electrophiles are involved, or these nucleophiles attack over the electron deficient center, or where some acid base are also involved in the reactions. But here in pericyclic reaction there is no involvement of nucleophile, electrophile, acid base like this. Okay, so usually we are only dealing with the reactions takes place in presence of either heat or light. Now, so before starting in detail the pericyclic reaction, let me give you the introduction. And in introduction, I will tell you some of the features of these pericyclic reactions and the classification of pericyclic reaction, how we can analyze these pericyclic reactions. So, some of the features of these pericyclic reactions, if you will see some features, then one of the thing, this pericyclic reaction, they are the concerted reactions, where all of you know this concerted reaction means bond breaking and bond formation occur in a single step with the formation of one transition state. So these are the concerted reactions. These are concerted reactions where bond breaking and bond formation occur in a single step. That is, bond breaking and formation take place in a single step. With the formation of one transition state only. Of one transition state. Okay, so these are the concerted reactions. And if you will see, means one transition state means, suppose if we see the energy profile diagram, if you will see the energy profile diagram, and if this is the reactant, here if reactant, then reactant will acquire some activation energy. So how this activation energy we will get in case of pericyclic reactions? This activation energy will get in presence of heat and light. After getting the minimum energy, after crossing the energy barrier to activate the molecule, then here the molecule get activated and then that will be converted into the product. So here only one transition state is formed in such reactions. Okay, and next, that here the cyclic shift of electron will take place. Pericyclic means there is a cyclic shift of electron along the periphery of the reactant molecule. Okay, so you will see in mechanism, you will see the cyclic shift of electron will occur. So there is a cyclic shift of electron, cyclic shift of electron along the periphery of the reactant. That is called as a pericyclic reaction. Okay. Reactant molecule. Next thing, as what I have told you, this reaction occur with the formation of transition state. Okay, and or we can say there is no role of here, no formation of intermediate occur. Otherwise, in organic reactions, you have seen various intermediate may be formed. For example, carbocation, carbanion, or radical intermediate, carbene, nitrene. These intermediates are formed, but here no intermediates are formed. No intermediates are formed. Okay. And another thing next, that there is no role of acid base, nucleophile, electrophile. There is no role. Okay, no role of acid base, or we can say nucleophile, electrophile. Okay, so there is no role of these things. Okay. It means how the reaction occur? Reaction occur in presence of heat and light. Reaction occur in presence of heat or light. Okay. Now, so when reaction occur in presence of heat and light, then here in such reaction the stereochemistry will also depend upon the heat and light. One molecule, if reactant molecule is there, then if reactant if in presence of heat, it can give you the one stereochemical product, or in presence of light it may give you the another stereochemical product. So stereochemistry depends upon the heat or light. Stereochemistry of product depends upon heat or light. Okay, so now, so next point, that one of the very important point here, if you will see the reactant and product, then the symmetry of orbitals of reactant and product, that will remain same. Okay, so in pericyclic reaction there is a conservation of orbital symmetry in reactant and product. So what does it mean? Suppose if reactant is having, the orbitals of reactant is having C2 symmetry or sigma mirror plane symmetry, then product, or the orbitals of product will also have the C2 and or mirror plane symmetry. Okay, so means here the conservation, the orbitals, the symmetry of the orbitals is conserved. Okay, so here the symmetry of orbitals in reactant and product is conserved. Symmetry of orbitals of reactants and product is conserved. That is, we can say that the orbitals of reactant as well as the orbital of the product have the same symmetry. Okay, that is, we can say orbitals of reactant and the orbitals of the product and orbitals of product will have the same symmetry. Or we can say symmetry element. Same symmetry, for example, it will have the same C2 symmetry or it will have the same mirror plane symmetry. So we will discuss it later on in detail, how the symmetry of reactants, the symmetry of orbitals of reactant and symmetry of orbitals of the product remain same. So we will see it in detail in different reactions, electrocyclic reaction. When we see the different type of pericyclic reaction, then we will see it. Okay, so these are some of the main features of pericyclic reaction. So what I have told you, mainly the pericyclic reaction, they occur in presence of heat or light. And another important point, the symmetry of orbitals of reactant and product, they are conserved. Okay. Now, to such type of reaction, it was first proposed by Woodward and Hoffman in 1965. In 1965, Woodward and Hoffman, they proposed this pericyclic reactions. Okay, they proposed the pericyclic reactions. So let's now come to the main classification of pericyclic reaction, and this mainly the pericyclic reactions are classified in a three type, that is electrocyclic reactions, cycloaddition reactions and sigmatropic reactions. So let's come to the classification. classification. So first is the electrocyclic reactions. Electrocyclic reactions. So what are these electrocyclic reactions? Here I will give you the brief of this, then we will see the details of this electrocyclic reactions. So in electrocyclic reactions, ring opening and ring closing or ring opening occur at the expense of one pi bond. So what does it mean? So I will understand you with the help of example. So here ring opening or ring closing occur at the expense of one pi bond. One pi bond. It means, what does it mean? If the reactant has 2 pi bond, then the product will have the 1 pi bond. That is, 1 pi bond will get decreased in the product. So either here ring closing will occur or ring opening reactions will occur in electrocyclic reactions. Now for example, if you will see, then suppose it is butadiene, and here this in presence of either heat or light, the ring closing of this will occur. And what I have told you, there is a cyclic shift of electron takes place in pericyclic reaction. So when this molecule will acquire the energy, then this pi electron cloud, which is the loosely held electron, they will shift, and they will shift such that the ring will get closed. So here first of all, and what I told you here, one of the transition state is formed. So transition state is formed, it means here the double bond is forming, whereas this pi bond get broken and this pi bond is broken here, and new sigma bond is formed. So this is the new sigma bond is formed, and I have it like this. So this is the transition state which is formed, formation, and where the bond formation and the bond breaking is shown here. So this cyclobutadiene, in presence of heat and light, it will undergo ring closing reaction, and what will be formed? Here you will get one of the double bond, and you will get the cyclobutene. Cyclobutene is formed. So here if you will see the number of pi bond, here you will see the number of pi bond is 2 pi bonds are present. Okay, 2 pi bonds are present, 2 pi bonds, and here if you will see only 1 pi bond is present. And one of the new sigma bond is formed here. This is the new sigma bond is formed, plus one new sigma bond, and plus one ring is also formed. So this is one of the examples. Similarly, if you will take, suppose I take so this is the hexatriene. Okay, hexatriene in presence of heat and light. What will happen? The cyclic, when it will acquire the energy, cyclic shift of electron will start at the periphery of this reactant molecule, and you will get such type of transition state. And what you will get? You will get the cyclohexadiene. So one double bond is created over here, another double bond is created over here, whereas new sigma bond is formed over here. So in this case, you can see 3 pi bonds are present. In product, 2 pi bonds are present, whereas one new sigma bond is formed, plus one new ring is formed. So you will see, overall if you will see, then what you are seeing, that inside electrocyclic reaction, 1 pi bond will get decrease in the product, and one new sigma bond and one new ring that would be formed. So overall rule, what does it tell? The overall, what we can say, if there is n pi bonds are present in reactant, then the ring closing or ring formation that will occur, ring closing or ring formation. So it may be this the reversible one. This can also be opened and this can also be closed. So if you will see, then number of pi bond is decreased by 1 and one sigma bond, new sigma bond is formed, plus one new ring is formed in such reaction. Okay, so it means if you see, if you are given, if you are told to find out whether what type of this pericyclic reaction is there, then if you see the reactant and product which follow this rule, then you will see, you can say that this reaction is a pericyclic reaction. So if this rule is followed, and that reaction would be the pericyclic, then that reaction would be the electrocyclic reaction. Okay, so this is about the electrocyclic reaction. Now next classification, that would be the cycloaddition reaction. Next type of reaction that we will study, that would be the cycloaddition reaction. Okay, so usually this electrocyclic reaction, they occur in a conjugated system. If you will see this conjugated type of system, you will see such reactions may occur. Or it may occur in some strained ring system, where the ring can be opened easily. Yeah, or strained ring system, then where the ring can open easily, strained ring, that where there also the reaction, such type of reaction may occur. Now next type of reaction, that is the cycloaddition reaction. In cycloaddition reaction, you will see here only one reactant is present. In cycloaddition reaction, two pi bonds react. Two pi bonds react together, and in product each two pi bond system will react, and in product you will see that in each pi bond system, in each means if suppose two pi bond systems are there, then they will form a ring, and in product the number of pi bond that will be decreased by the 2. Okay, so here in product number of pi bond is decreased by 1, whereas in cycloaddition reaction, in product number of pi bond that would be decreased by 2. So here two reacting partners, two pi bond system react. So in this case, two pi bond system react. Two pi system react together to form a ring. At the expense of one pi bond in each reacting partner. So in each reacting partner, one pi bond will get decreased. In each reacting partner, the one pi bond will get decreased, or you can say overall, you can say in product two pi bond will get decreased. So suppose if you will see the example, and if you have the simplest example where two ethene system, two pi systems are there, and these are the same pi system. If they will react in presence of heat or light, then what will happen? A cyclic shift of electron will start. The pi bond being the loosely held electron, they will start moving, and it will form a ring like this. It will form a cyclobutane in this case. So if you will see here, then number of pi bond is one pi bond, here also one pi bond, whereas total number of their pi bonds are 2, and in product the 0 pi bond is present. So 0 pi bond is in product, and you will see two new sigma bond is formed. Over here, and plus one ring is formed. So two new sigma bond plus one ring is formed. In the same way, suppose I take the example of another cycloaddition reaction. In another cycloaddition reaction, if you will see, then if you have this pi system, and another pi system. This is one of the diene, and this is dienophile. You can say this is diene and this is dienophile, like a Diels-Sade reaction. So this in presence of heat and light, so cyclic shift of reaction will start. This moving here, then these electrons will go over here. This reaction electrons will go over here, and you will get what you will get. These are the two new sigma bonds which are formed, okay, and one new pi bond which is formed over here. One new pi bond is formed. So this contains two pi bond, this contains one pi bond, and overall this contains, to total 3 pi bonds are present in a reactants, whereas number of pi bond in a product is only one pi bond. So overall, if you will see, the total number of pi bond is decreased by 2, and plus 2 new sigma bond plus 1 ring is formed. So overall, what you can see in cycloaddition reaction, in overall conclusion is that if you have n pi bond in reactant, then n pi bond in reactant, and in product you will have always n minus 2 pi bonds plus 2 new sigma bond plus 1 ring that would be formed. So in this way we can differentiate the electrocyclic reaction and cycloaddition reaction on the basis of this general rule. Okay, so if you will see the reactant and product which follow this rule, it means this is the cycloaddition reaction. There the cycloaddition reaction occur. Where in reactions where such rule is followed, then the electrocyclic reaction that will takes place. Now let's see the third classification. Now third classification, that is sigmatropic reaction. Sigmatropic reaction. Now in sigmatropic reaction, what you can see, sigma bond migrate. Okay, from this name sigmatropic, you can say here the sigma bond will migrate. Here also we take the pi system. So the sigma bond will migrate in pi system from one center to the another center, or from one terminal to the another terminal. So here migration of sigma bond occurs. So sigma bond migrates from one end to the other end of the pi system. Okay, from one end to another end the sigma bond will migrate, and in such reaction there is no change in the number of pi bonds. Okay, net pi bond remains same, and net number of pi bonds remains same. Net number of pi bond as well as ring, and ring remains same in reactant and product. In reactant and product. So here sigma bond migrates, and the number of pi bonds or number of rings that remains same in reactant and product. So let's see the example. If you will see the example, suppose I take one of the pi system. Suppose this is our deuterated system. Deuterium is present in place of hydrogen, or deuterated pentadiene. So this in presence of heat or light. what will happen? The sigma bond will migrate. So here this one of the sigma bond, this sigma bond from one end, okay, this contains the 2 electron, and the deuterium will with its 2 electron that will migrate to the another end of the pi system. So this is one end of this pi system, this is the another end of this pi system. So this bond, this sigma bond will migrate from one end to the another bond. So how it will migrate? So when it will acquire energy, this pi bond being the loosely held, it will cyclic shift of electron will start. So this electron will go here, it will go over here, and this bond will break, and the pi and sigma bond will migrate. Okay, so what would be the product? So if you will see the product, so product, that single bond will come over here, and one of the deuterium that will attach over here, it will acquire the double bond here. This bond will get the single bond, this will be converted into single bond, this would be converted into double bond, and 2 deuterium, these are present over here. So such type of product that would be obtained. Now if you will see, then what type of this sigmatropic reaction is this? So if you will see, then for this we should number it, and it is a allylic system. Allylic system means this is the sp2 hybridized carbon, and this is the sp3 hybridized carbon. Okay, so when there is a sp3 hybridized carbon is present in the neighbor of sp2 hybridized carbon, then this carbon, the sp3 hybridized carbon, that would be called as the allylic carbon. So this is sp2, this is sp3. So the carbon which is near the sp2 hybridized carbon, which is means this sp3, that would be called as the allylic carbon. So this would be the allylic carbon. So this carbon would be the allylic carbon, this would be the allylic carbocation, this would be the allylic carbanion, or this would be the allylic radical. So here this is your sp2 hybridized, and this is your sp3 hybridized carbon. So like this. So this is, so how we can categorize, how we can name this sigmatropic reaction. So if you will see, then in such reaction, the allylic carbon is given number 1. Okay, allylic carbon is given number 1. Then from here we will start number 1, 2, 3, 4, 5. So number 1 carbon, number 2 carbon, 3, 4. And this may be given also 1 dash or 1, this deuterium which will migrate. So this first to 5th migration, sigma bond is migrating from 1st carbon to the 5th carbon. That's why it can be named as 1,5 sigmatropic reaction. And in such reaction, number of pi bond that remains same, number of ring that remains same in reactant and product. 2 pi bonds, here also 2 pi bonds. Okay, and the same way, so this is an example of 1,5 sigmatropic reaction. So suppose I take this one. Then here, what type of shift you can see here? You will see that this would be the allylic carbon. So that is given number 1, this is 2, this is 3, and this would be the, so this is this would be the reactant molecule. This is suppose reactant molecule. This is the allylic carbon, 1st carbon, 2nd carbon, and this will be the 3rd carbon. So the sigma bond migrates from one end of the pi system to the another end of the pi system, and what you will get here, you will get, so there, like this. So double bond will be created over here, and you will get one of the deuterium will come over here. So the sigma bond is migrating from 1st carbon to the 3rd carbon. That's why this is an example of 1,3 sigmatropic shift. 1,3 sigmatropic shift. Here also this from 1st carbon, this sigma bond may migrate to this 3rd carbon also. But whether this is feasible or not, whether this reaction is feasible or not, the migration from first to third is possible or not. So we will see when we will discuss the sigmatropic reaction in detail. So these are the three main categorization of the pericyclic reaction. Now, otherwise we also read about the group transfer reaction. Now this is the next category. Okay, group transfer reaction. In group transfer reaction, this sigma bond, their migration of sigma bond occur from one molecule to the another molecule. Okay, so the sigma bond migrate from one molecule to the another molecule. So migration of sigma bond from one molecule to the another molecule. Another molecule. Okay, so if you will see, then suppose this is one of the system and this is the another pi system. Two pi system are there. Okay, and in this 2 pi system, if you will see, then this is the allylic system. This is the allylic system, and this is the another pi system. This is the another pi system. Two type of system you will take in group transfer reaction. One should be the allylic system, another this type. Now in this case, after acquiring the heat or light, what will happen? So this electron will go over here, cyclic shift will start. This sigma bond will move at this position and this electron will come over here, and you can see the cyclic shift of reaction, and the double bond, new double bond is created over here. This double bond is converted into single bond. One of the new sigma bond is formed over here, this new sigma bond, and here double bond is converted into single bond, and another new sigma bond is formed over here. Two new sigma bond is formed. So this is somewhat similar to the cycloaddition reaction, where two new sigma bond is formed, and it is also similar to this sigmatropic reaction where the sigma bond migrates. Okay, sigma bond migrates, but here only two molecules are present. Here one molecule is present as in a reactant system. Okay, so this is, or otherwise sometimes the metal also migrate in this. Here the hydrogen atom is migrating, but sometime in place of this hydrogen atom, metal may also migrate. This may also be the metal. Metal can also get migrated. So this is an example of group transfer reaction, and next one we will study, that is the kilotropic reaction. So in kilotropic reaction, this is also another characterization. In kilotropic reaction, we will see the mechanism of this reaction also. The single atom is involved in the formation of ring with the another pi system. Okay, so single atom forms ring with some pi system. Okay, so for example, suppose if we have ethene and if we have this is carbene, then such type of reaction this will occur over here, and we will get a cyclic ring that would be formed in such way, the ring that would be formed over here. So this reaction is an example of the kilotropic reaction. We will see more examples in kilotropic reactions. So now these pericyclic reactions, they what type of mechanism they will have. So mechanism of such reaction that can be understood by some of the methods. So let's see some of the methods. So methods of analyzing such reaction. So in methods of analysis, one of the method is we will see the conservation of orbital symmetry method. Conservation of orbital symmetry method. Okay, conservation of orbital symmetry method or orbital symmetry correlation method. So this is also called as the orbital symmetry correlation method. Correlation method. In this method, you will see the orbitals of same symmetry in reactant and product, they are correlated. So just for in a single line that I can say, otherwise we will see in detail. So orbitals of same symmetry in reactant and product, they are correlated. So this we will done in because I have told you in features of pericyclic reaction, what I have told you, the reactant and orbitals should have the same symmetry. Reactant orbitals and product orbitals should have the same symmetry. So one of the method of analysis where the orbitals of same symmetry in reactant and product are correlated, and this was given by Woodward and Hoffman. Woodward and Hoffman, they give this method of analysis. Second method that we will study, that is frontier molecular orbital method. Frontier molecular orbital method, and in short we say it a FMO method, frontier molecular orbital method. So here we know that two frontier orbitals are there. One is called the HOMO and another called as the LUMO. So HOMO and LUMO, they are considered during the analysis of these reactions. HOMO and LUMO are considered, they are involved in the analysis of such reaction. Okay, so frontier orbital molecular orbital method, it was given by Foucault. Okay, and the third method that is the we say PMO method or Huckel-Mobius method. Huckel-Mobius method. In short, we can write it HT method, Huckel-Mobius HM method, or it is also called as the PMO method, perturbation molecular orbital method. Perturbation molecular orbital method, which is called as the PMO method. Okay, so this was given by the Zimmermann and Dewar. So it was given by H. Zimmermann and Dewar. So these are the three ways by which we will analyze the electrocyclic reaction, cycloaddition reaction, sigmatropic reactions. So in my next lecture, I will start from the electrocyclic reaction, and before that, I will tell you how we can make the molecular or pi molecular orbitals. So how we can draw the pi molecular orbital diagram for ethene system, for hexatriene, or for octatetraene system. So how can we draw the pi molecular orbital diagrams for the different conjugated system, as well as some of the different allylic allylic system that we will see. Okay, thank you.